Okay. Now, I carelessly wrote down, at first I wrote down KE2 over KE1. KE2 being the kinetic energy of the two objects after collision, KE1 being the kinetic energy of the two objects before collision. Now, usually we would do the ratio KE2 over KE1, not KE1 over KE2. I did originally write KE2 over KE1, then I proceeded to write KE1 on top and KE2 on the bottom, just being careless. So I had to change my subscripts, but I changed them back here. So don't let that confuse you. You will accept that KE1 is the kinetic energy of the first object, which is 1/2 the mass of the first times its velocity, m1 times the square of 4 meters per second. And I said times its velocity times the square of its velocity. And for the second object, I write it down even though I know it's 0, because we want to get in the habit of writing everything down. So it's 1/2 the mass of the second, which is 1.5 m1, times the velocity before the collision squared. Well, that's 0, so this is all going to give us 0. And then I do a similar thing with the KE2. The second object is now at rest, so I have 1/2 m1 times 0 squared for that kinetic energy. And the second object is moving at 2/3 of your 4 meter per second velocity. And you notice I didn't ever work that out because nobody ever asked what the velocity was, just what the ratio of velocities was. So there's no need to actually write that out as 8/3 of a meter per second or 2.66 ... or 2.67 approximate. We just kept the 2/3 in here, okay? And you'll see how that turns out to be a handy thing to do. So anyhow, there's the velocity of the second object, there's its mass, and there's the 1/2, so there's the kinetic energy of the second mass after collision. Now, I flip this back the way it should, so that what's in the denominator here is going to end up in the numerator, what's in the numerator here will end up in the denominator. It's not hard to follow that. You got the zeros here and here. What's in the denominator here is just this then. What comes from in the numerator is going to be just this. And if we look at what we've got, we see that the m1 divides the m1. The square of 4 meters per second divides the square of 4 meters per second. Now I did do one little thing when I wrote this down, and I didn't mention it. Squaring 2/3 of 4 meters per second is the same as multiplying the square of 4 meters per second by the square of 2/3, right? And I did that so I could clearly see that this and this are the same, so they just divide out and give you 1. These m1s divide out and give you 1. The 1/2s divide out and give you 1. I don't like the word cancel, people do it wrong. Leaving me with the 1.5 and the square of the 2/3. That's all. And of course 1.5 is 3/2. You multiply it by the square of 2/3, you get 2/3. You should see that instantly, but if not, work it out, and next time you see something like that, be sure you do. It's very simple. Now again, all we asked was, is kinetic energy conserved? I chose to prove that it wasn't by taking the ratio of the kinetic energy after to the kinetic energy before. I find that you only have 2/3 of the kinetic energy after collision that you had before. And so the kinetic energy isn't conserved. Collision isn't elastic. Energy conservation, on the other hand, is just fine. You lost 1/3 of your kinetic energy somewhere. Well, that probably went to heating up the two objects, because when they compress, you're bunching up the atoms, causing something like friction between them. That's not exactly what's going on, but and that heats them up. Also, there's a little bit of sound. The sound energy is not all that great. Mostly the heating of the two objects when they compress and decompress. Okay, and in any case, okay, collision isn't elastic. Okay, well now we want to analyze what would happen with the same initial velocity and the same masses. Same initial velocities, this one at rest, this one at 4 meters per second, same ratio of masses. What would happen if the collision was elastic. So we want to talk about what that means, and relative velocities and a couple of other things so we can get a handle on the elastic collision.